Crystals are fascinating structures. We encounter them every day, from the ice in our drinks to the salt we sprinkle on food. These materials are defined by their repeating patterns in space. Imagine a grid of atoms arranged in a precise repeating order. This spatial order is what gives crystals their unique properties, but what if this order existed not just in space, but in time? What if we could create a structure that repeated itself, not across a distance, but across a period of time? This is the revolutionary idea behind time crystals. In 2012, Nobel laureate Frank Wilczek proposed the existence of these exotic phases of matter. He envisioned structures that would exhibit a repeating pattern in their lowest energy state, a state normally associated with stillness and equilibrium. This proposal sent ripples through the scientific community, challenging our understanding of the very nature of time and order. Could a system truly exhibit perpetual motion without any external energy input? The quest to create and understand time crystals began. To grasp the concept of time crystals, we need to delve into the realm of spontaneous symmetry breaking. In physics, symmetry refers to a system's ability to remain unchanged under certain transformations. For instance, a perfect sphere is symmetrical because it looks the same no matter how you rotate it. Spontaneous symmetry breaking occurs when a system in its lowest energy state, known as its ground state, does not exhibit the same symmetries as the laws that govern it. A classic example is a ferromagnet. Above a certain temperature, the magnetic moments of its atoms are randomly oriented, exhibiting rotational symmetry. However, below this temperature, the moments spontaneously align in a specific direction, breaking the symmetry. Time crystals take this concept a step further. Instead of breaking spatial symmetry, they break time translation symmetry. This means that their properties oscillate periodically over time, even in their ground state. Imagine a pendulum that never stops swinging, even without any external force. To describe these systems theoretically, physicists employ tools like the Floquet formalism. This mathematical framework helps analyze the behavior of systems driven by periodic forces. Another crucial concept is many-body localization. This phenomenon occurs in disordered systems, where particles interact strongly with each other, but are localized due to the disorder. Many-body localization can protect the delicate time crystalline order from collapsing under its own dynamics. Frank Wilczek's 2012 proposal of time crystals was met with both excitement and skepticism. Could a system truly exhibit perpetual motion without violating fundamental physical laws? Initial analyses suggested that equilibrium time crystals, those existing in their ground state, were impossible. However, the scientific community didn't give up. Researchers quickly realized that non-equilibrium systems, those driven by external periodic forces, could potentially host time crystalline behavior. This shift in focus led to a surge in theoretical and experimental efforts. Early theoretical models focused on systems like rings of trapped ions or spins in a magnetic field. These models showed that under specific conditions, these systems could indeed exhibit periodic oscillations, even when driven at a different frequency, a hallmark of time crystals. The theoretical breakthroughs paved the way for experimental realizations of time crystals. In 2016, two independent groups reported the first experimental observations of these exotic phases of matter. One group used a chain of trapped ytterbium ions, while the other employed nitrogen vacancy, NV, centers in diamond. Both systems shared key features. They were periodically driven by external forces and exhibited oscillations at twice the driving period, a signature of time crystalline behavior. These experiments marked a turning point in the field. They not only confirmed the existence of time crystals but also opened up new avenues for exploring their properties and potential applications. Section 5. Modeling Time's Rhythms. Unveiling the Mathematics of Time Crystals. To understand the intricate workings of time crystals, physicists rely on theoretical models. One such model is the periodically driven spin chain. Imagine a chain of atoms, each with a spin that can point up or down. These spins interact with each other and are also subjected to a periodic magnetic field. the Hamiltonian, a mathematical operator that describes the system's energy. For this model can be written as h of t equals the sum of j sub ijs sub izs sub jz plus h of t times the sum of s sub ix, where j sub ij represents the interaction strength between spins I and j, s sub iz and s sub ix are spin operators for spin I, and h of t is the time-dependent magnetic field. This seemingly simple model captures the essence of time crystals, exhibiting spontaneous symmetry breaking and oscillations at a subharmonic frequency of the driving field. By studying such models, researchers gain insights into the stability, properties, and potential applications of time crystals. Section 6. Time Crystals and the Future. Revolutionizing Physics and Technology. The discovery of time crystals has profound implications for various fields, from fundamental physics to quantum technology. In fundamental physics, time crystals challenge our understanding of time itself. They provide a unique platform to study spontaneous symmetry breaking, non-equilibrium phenomena, and the interplay of quantum mechanics and general relativity. In quantum computing, time crystals offer a new paradigm for storing and processing information. Their inherent robustness against decoherence, a major obstacle in building quantum computers, makes them attractive candidates for quantum bits, or qubits. Furthermore, time crystals hold promise for applications in metrology, enabling the development of ultra-precise clocks and sensors. Their sensitivity to external perturbations could lead to advancements in medical imaging, navigation, and materials science. Section 7. Unlocking Time's Secrets, Challenges and Mysteries on the Horizon. Despite the remarkable progress, the field of time crystals is still in its infancy. Many challenges and open questions remain, fueling ongoing research efforts. One challenge lies in achieving long-lived, time crystalline order. While current experiments have demonstrated time crystals that persist for relatively short periods, extending their lifetime is crucial for practical applications. Another hurdle is scalability. Most experimental realizations involve small systems with a limited number of particles. Developing larger and more complex time crystals is essential for exploring their full potential. The question of whether equilibrium time crystals can exist remains open. While theoretical limitations exist, some proposals suggest that these elusive phases of matter might be possible under specific conditions. Section 8. The Allure of Time Crystals, a glimpse into the quantum future. Time crystals, once a theoretical curiosity, have emerged as a vibrant field of research with far-reaching implications. Their discovery has shattered long-held assumptions about the nature of order and time itself. These exotic phases of matter offer a glimpse into the weird and wonderful world of quantum mechanics, where the impossible becomes possible. Their ability to break time translation symmetry, exhibiting perpetual motion without energy consumption, challenges our classical intuitions. The exploration of time crystals is still in its early stages, but the discoveries made so far have ignited a sense of wonder and excitement within the scientific community. As we delve deeper into this uncharted territory, we can expect even more surprises and breakthroughs that will reshape our understanding of the universe. Section 9. Beyond Imagination. Time crystals and the expanding frontiers of science. The journey of time crystals embodies the spirit of scientific exploration. It began with a bold idea, a spark of imagination that dared to challenge the established order. This idea, initially met with skepticism, gradually gained traction as theoretical frameworks were developed and experimental evidence emerged. The discovery of time crystals is a testament to the power of human curiosity and ingenuity. It reminds us that the universe is full of wonders waiting to be uncovered, and that the boundaries of our knowledge are constantly expanding. As we continue to unravel the mysteries of time crystals, we embark on a journey that transcends the boundaries of traditional disciplines. This quest will undoubtedly lead to new discoveries, not only in physics but also in materials science, quantum information processing, and beyond. The future of time crystals is bright, filled with possibilities that stretch the limits of our imagination. Who knows what other secrets of time and matter await us as we venture further into this uncharted territory? Only time in its own enigmatic way will tell.